This is Bob Capetta, and this lesson is an introduction to probability. So here's our first concept. A sample space is the set of all equally likely outcomes. So what does that mean? Our simplest case is to flip a coin. If you flip a coin, there's two things that could happen. You could get heads, you could get tails. Both are equally likely, so that's what makes up the sample space. If a die is rolled, what are the possible results? You could get 1, 2, 3, 4, 5, or 6, all equally likely. Equally likely outcomes make up the sample space. Now, if 2 dice are rolled, the sample space is not 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, those are all the possible outcomes. But why is that not the sample space? We've listed all the things that could happen. The lowest sum you can get from 2 dice is 2. The greatest sum you can get is 12. But why is that not the sample space? Well, the answer is they're not equally likely. A 7 is much more likely than a 2 or a 12. So we cannot list all the outcomes and assume they're equally likely. We need to figure out some way to describe that process. So how can we construct a sample space that reflects 2 dice? Well, what I'm going to do is I'm going to think about a red die and a blue die. So I'm going to list all the numbers in pairs. The first number corresponds to the red one. The second number corresponds to the blue one. So you could have a 1 on the red one and a 1 on the blue one. You could have a 1 on the red die and a 2 on the blue die. You could have a 1 on the red die and a 3 on the blue die. So here's all the possibilities. First one is red, second one is blue, just so we can think about these things representing an order of sorts. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, up through 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. These are all equally likely outcomes. 36 possibilities. Now, we said earlier that all the possible totals are 2 through 12. You'll notice the only way you're going to get 2 is if 1, 1 shows up. The only way you're going to get 12 is if 6, 6 shows up. But look at how many ways you can get 7. 6 plus 1, 5 plus 2, 4 plus 3, 3 plus 4, 2 plus 5, 1 plus 6. So the numbers 2 through 12 are all the possible outcomes, but they are not all the equally likely outcomes. To describe the sample space, I need to do it this way. How about flipping 2 coins? Well, let's think about that. You flip 1 coin, your possibility is either a heads or a tails. What about if you flip 2 coins? Well, if the first is heads, second one could either be heads or tails, which means you get heads, 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 tails. If the first is a tails, second one could either be a heads or a tails, so you get tails, heads, tails, tails. Let's put those together. What do we have? Heads, 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 tails, tails, heads, tails, tails. Those are the 4 equally likely outcomes that reflect flipping 2 coins. Okay, we're going to go from there to the notion of probability. So the informal notion is if you're determining a theoretical probability, count the number of winners divided by the number of total possibilities. So here's our formal statement, computing theoretical probability. If an event E has n of E equally likely outcomes, and its sample space S has n of S equally likely outcomes, the theoretical probability of event E, denoted by P of E, is the number of outcomes in E divided by the number of possible outcomes. Again, informally, number of winners divided by total. But the only way this works is if you list your sample space with all equally likely outcomes. So here's our first example. If a coin is tossed, what is the probability of getting heads? Well, our sample space is just heads or tails. Our event is just heads. So number of winners divided by total, well, our event is heads. Again, sample space heads, tails. So the number of the event is 1. The number in the sample space is 2. So the probability of heads, which is the probability of the event E, is just 1/2. Let's look at another one. If a die is rolled, what is the probability of getting a number more than 4? So remember our sample space, 1, 2, 3, 4, 5, 6. Which one of those are more than 4 to define our event? That would be 5 and 6. So that's our event, but our sample space again, 1, 2, 3, 4, 5, 6. So the probability is the number of winners, the number in the event, divided by the number in the sample space. The number in the event, 2 of them. The number in the sample space, 6 of them. So we get the probability of that event being a number more than 4 is 2 out of 6, 2, 6, which reduces to 1/3 for our probability. Next up, if 2 coins are tossed, what is the probability of getting 2 tails? So tails, TT. That's the only way you're going to get 2 tails. Tails, tails. What was your sample space? We recall heads, 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 tails, tails, heads, tails, tails. Notice this event is a subset of the entire sample space. How many winners in the event? Just 1. How many total in the sample space? 4. So our probability of that event of getting 2 heads is 1 out of 4. 1 winner out of 4 total. Then I'm going to say if 2 dice are rolled, what is the probability of getting a sum of 9? So remember, I cannot just write down 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 because those are not equally likely. I've got to go 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, etc. So there is the sample space that corresponds to rolling 2 dice. Now, where are the ones that give us a total of 9? Well, here's the first one I see, 3 plus 6. Another one, 4 plus 5. 5 plus 4. 6 plus 3. So that's how many of them? 1, 2, 3, 4. So there's my event. There's my number of winners. 3, 6, 4, 5, 5, 4, 6, 3. And there is my sample space. So the probability of that event is the number of winners divided by the number in the sample space. The number of winners, 1, 2, 3, 4. The number in the sample space, 36. So the probability of that event is 4 out of 36, which is 1 out of 9. So all the examples we've done so far have been based on this notion of theoretical probability, right? So we had this notion, but that only works if we can describe an experiment in all of the equally likely outcomes. But in reality, we do a lot of observations, and from those observations we can determine probabilities in a slightly different fashion using something called empirical probability. A minor difference, but let's take a look at an example. All high school freshmen at a high school take one of the following math courses: pre-algebra, algebra 1, or geometry. The following table describes the semester grades for each course. So we have A, B, C, D, F, pre-algebra, algebra 1, and geometry. So these are the various students in each group. So 4 students took pre-algebra and earned an A. 6 students took pre-algebra and earned a B. 22 students, for example, took algebra 1 and earned a C. 1 student took geometry and earned a D. We want to ask a question. What question are we going to ask? If a student is selected at random, what is the probability that that student is enrolled in pre-algebra? Well, how many pre-algebra students do we have? 4 plus 6 is 10, plus 8 is 18, plus 2 is 20, plus 1 more is 21. So we're still thinking winners divided by total. So 21 winners, 21 students in pre-algebra divided by the whole group, whatever that is. Now, I've actually totaled those here. So you can see indeed we have, indeed we have 21 in pre-algebra. We have 59 in algebra 1, 17 in algebra 2, 97 students total. So here is our formula for empirical probability, which looks very similar to our formula for theoretical probability, although we don't really have a sample space, all equally likely outcomes, but every student selected at random is equally likely to be selected. But our notion tells us that the empirical probability is the number of observed time the event occurs divided by the total number of observed occurrences. So it's essentially the same concept. How many pre-algebra students do we have? 21 divided by how many students total? 97. So the probability of that event, as in taking pre-algebra, 21 out of 97, or 0.2165. 4 decimal places is the standard used for probability, so it's not a bad idea to think of it that way. Now, if a student is selected at random, what is the probability the student gets a grade of D or F? So we have D students, 7 D students, and 4 F students. So any student selected at random, any one of the freshman class, 7 earned D, 4 were given an F. So 7 plus 4 total, or 11 out of 97, 11 quote-unquote winners, hard to call D's and F's winners, but 11 in our event divided by 97 total gives us 11 97ths, or approximately 0.1134. Next up, I'm saying if a student is selected at random, what is the probability the student is a pre-algebra student who earned a grade of A? So this time I want the student to both be a pre-algebra student and an A student. And the only people that satisfy both of those conditions are the 4 people right here, pre-algebra and A. Pre-algebra and A, the number in our event is 4 out of how many total? Out of 97, which gives us a decimal approximation of 0.0412. So that's in essence how empirical probability works. Let's take a look at one more example. This is an old piece of data. I am recording this video during the COVID-19 crisis. I'm sad to say our unemployment numbers currently are much worse than this. Let's hope they get better soon. So here's recent numbers from the U.S. Bureau of Labor Statistics. Employment status of the U.S. labor force, ages 16 or older in millions, people who are in the labor force. Unemployed means they are actively looking for a job. Employed means they have one. Not in the labor force means they're neither looking for a job nor employed. So we have these numbers. You'll notice a total of 116 men, 124 women, 140 employed people, 14 unemployed people, 14 million unemployed people, 86 million not in the labor force, 240 million people total in the U.S. labor force when this data was taken. So yes, indeed, in millions, 74 million, 66 million, 140 million. So our first question will be, find the probability that a randomly selected person from the labor force is female. So how many winners divided by how many total? How many winners? Well, 124 or 124 million, but since this is all in millions, we could ignore the million part. 124 in the event divided by 240 total. Probability of female, 124 divided by 240, or 0.5167. My next question is, find the probability that a randomly selected person from the labor force is unemployed. How many folks do we have that are unemployed? 14 million people are unemployed out of how many total? Out of 240 million. So for the unemployed, that's 14 divided by 240, which turns out to be about 0.0583. Again, it's pretty standard to use 4 decimal places for probabilities. Let's take a look at one more question. Find the probability that a randomly selected person from the labor force is a male who is employed. So which cell includes both men and employed? That would be this one right here. Male and employed, 74, male and employed out of how many total? Out of 240. So for employed and male, 74 out of 240, which is approximately 0.3083. And that will conclude this lesson.